Hey everyone, and welcome to The Explainer. I am absolutely thrilled you're joining us today because we're going to unlock some of the coolest secrets of temperature sensing. If you've ever found yourself wondering how all these smart devices around us literally feel the heat or the cold, well, you are completely in the right place. And the absolute best part? We're going to completely demystify this technology without getting bogged down in any complex math. So let's jump right in.
Now, think about your everyday life for just a second. How does your smart thermostat actually know when your living room is getting a little too chilly and it needs to kick on the heat? Or think about a massive deep freezer in a restaurant. How does it automatically send out a warning alert before thousands of dollars of food just spoils? We take this invisible environment totally for granted, right? But underneath the surface, there's always a tiny, unsung hero doing the heavy lifting to bridge our physical world with the digital one.
And that brings us perfectly to the star of today's explainer, the KY-013 temperature sensor module. This little piece of hardware is just incredibly versatile, and it's wonderfully affordable too. It is a massive favorite in the DIY and electronics community, mainly because of its huge operating range. We're talking about accurately measuring everything from a freezing -55 degrees all the way up to a literally boiling 125 degrees Celsius. And it does that with an accuracy of plus or minus half a degree. That is a massive range for something so incredibly small.
But here is where things get kind of wild. It's a bit of a plot twist, actually. It's this grand mystery in the world of hobbyist electronics. You see, depending on the specific manufacturer you buy from, this exact same module name actually houses two entirely different pieces of technology. Yeah, no joke. It might look really similar on the outside, but what's happening on the inside is fundamentally different.
Okay, let's dive into this. We're essentially looking at a tale of two sensors here. On one hand, you might get a version equipped with an analog NTC thermistor. But on the other hand, you might get a version featuring a digital DS18B20 sensor. One operates by physically changing its electrical resistance in an analog wave, while the other communicates by sending pure digital code. Understanding which one you have and how they both work is absolutely crucial. It's the key to mastering temperature sensing.
So let's look at version 1 first, the analog NTC thermistor.
Remember that no math promise from the beginning? I'm sticking to it for sure. NTC simply stands for negative temperature coefficient. All that really means is that as the physical temperature around the sensor goes up, its electrical resistance goes down. They work in exact opposites. So as your room gets hotter, the sensor basically allows more electricity to flow right through it. To read that changing resistance, the circuit uses something called a voltage divider. Imagine a stream of water that splits into two different pipes. One pipe is a fixed, normal size. The other pipe, which is our NTC sensor, magically shrinks or expands depending on how hot the room is. When that heat-sensitive pipe shrinks, the water pressure in the rest of the system changes. By simply measuring that changing pressure, or the voltage, your computer can figure out exactly how hot or cold it is. It's brilliantly simple, right?
Now there is a catch. The crucial point here is that this fluctuating voltage is an analog signal. But microcontrollers, like your computer, only think in ones and zeros, pure digital code. If you're using an Arduino, you're totally in luck. It has a built-in translator, called an ADC, or analog to digital converter, right there on the board. You just plug it straight into an analog pin, like A1. But if you're using a Raspberry Pi or maybe a microbit, you've got a slight challenge. They don't have native analog inputs. So to read the NTC sensor, you need to add an external translator to your circuit, something like the KY-013 ADC module, just to turn those analog waves into digital numbers your Pi can actually understand.
Moving right along to version 2, the digital DS18B20.
Unlike the analog version we just talked about, this brilliant little module does all of the complex conversion math right inside the tiny black chip right on the board. Because it handles the math internally, it outputs a purely digital signal using something called the one-wire protocol. To visualize this, just think of a single-lane digital highway. Instead of needing a massive, messy bundle of cables, all the digital data packets politely take turns driving down this one single lane to get to your microcontroller. It's just an incredibly efficient way to send complex data using the absolute minimal amount of wiring.
Wiring this up to an Arduino is beautifully simple. You've got a wire for 5 volts of power, a wire for ground, and just one data wire connecting over to digital pin D2. However, there is a very specific, absolutely essential tip to keep in mind here.
You crucially need a 4.7 k-ohm pull-up resistor placed right between the power line and the data line. Think of this as a stabilizer for our single-lane highway. It ensures the digital communication stays perfectly clear and doesn't just drop out on you.
Let's move on and see how this builds into an actual project. Getting this digital sensor to send data right to your computer screen takes just 4 incredibly simple step-by-step actions. Step 1. Connect your power, ground, and data wires. Step 2. Bridge that data line to power with your 4.7K pull-up resistor we just talked about. Step 3. Hop onto your Arduino software and install the one-wire and Dallas temperature code libraries. And Step 4. Just upload the code and read the data. Seriously, within minutes, you go from a pile of parts on your desk to seeing real-time room temperatures scrolling down your screen.
So why does all this matter? Why go through the effort of setting this whole shebang up? Because it empowers you to build those real-world applications we talked about at the very beginning. With this incredibly affordable little module, you can build your own smart home climate monitor to keep your house energy efficient. You can automate an entire greenhouse, making sure your plants have the exact temperature they need to thrive. You can log local weather data. Or you can build that awesome freezer alarm to ensure food safety by tracking internal temperatures. The applications are practically endless. Really.
Well, we have definitely covered a lot of ground today, from the shifting resistance of analog NTCs to those single-lane digital highways of the DS18B20. You now know exactly how these tiny devices bridge the gap between the physical heat of the room and the digital brain of a computer. So my final question to you is this. Armed with a simple KY-013 and an Arduino, what invisible environment will you start measuring today? The power to build your very own smart sensors is literally right there in your hands. Get out there, start tinkering, and I will see you in the next explainer.
Hey everyone, and welcome! Today, we are demystifying one of the most misunderstood, confusing, yet absolutely fascinating components in the electronics world, the KY-013 temperature sensor. Whether you're a maker just starting out or an engineer designing complex systems, knowing your hardware inside and out is literally the key to success. So let's dive right in and decode this mystery together.
Right off the bat, we run into what we call the identity crisis, and it's the absolute heart of the confusion. There are actually 2 completely different modules sold under the exact same KY-13 label. You hit order online, and you might receive a 20th century analog component, or you could get a 21st century digital microchip. They both measure temperatures from -55 to +125 degrees Celsius, but their internal designs, how they work, and the language they use to talk to your microcontroller, totally different.
So ask yourself right now, which sensor is actually in your hands? If your code is throwing errors or you're getting total garbage data, the problem might not be your code at all. It might just be that you're speaking the wrong language to your hardware. Figuring out exactly what you have is your very first step to engineering mastery.
Here is our roadmap for today's explainer. We'll start with the KY-013 identity crisis, look at the analog versus digital collision, walk through a step-by-step Arduino wiring guide, tackle the Raspberry Pi communication barrier, cover some pro debugging tips, and finish up with real-world use cases.
Section 1. The KY-013 Identity Crisis.
It's literally a tale of 2 sensors. We've got one single name tag masking 2 completely different ways of sensing the physical world. On one hand, you have an analog setup where resistance changes physically with temperature. On the other, you have a smart chip that processes data internally and spits out neat little digital packets. Your microcontroller, the brain of your project, absolutely has to know which language it's listening to. Otherwise, you get a complete communication breakdown.
Section 2. The analog versus digital collision.
So, how do you actually tell them apart? The easiest way is just a visual check. Notice that little colorful glass-like bead? That's your analog NTC thermistor. Now look at the other variant. That black, flat-faced cylinder is the digital DS18B20 chip. They both sit on tiny boards with 3 pins, but their personalities couldn't be more different.
Let's break down the tech. Think of the analog NTC like a thermal seesaw. As the room gets hotter, its resistance drops, giving us a continuous, wavy voltage signal. Its precision entirely depends on your host device's analog-to-digital converter. But the digital DS18B20, it's basically a microscopic computer. It measures the temperature internally and converts it into pristine 9 to 12-bit binary data, just ones and zeros, sending it down a single wire. Interestingly, they both run on 3.3 to 5.5 volts, and both give you a super accurate reading within half a degree Celsius.
Section 3. Step-by-step Arduino wiring.
All right, let's get the digital version wired up. The pin marked with a minus sign goes straight to your Arduino's ground. The middle pin, usually marked plus or VCC, goes to your 5V power output. But the critical one is S, the signal pin. This is your main digital highway, and you'll want to connect it directly to Arduino's digital pin 2. All your data traffic is going to flow right down this single lane.
Once your hardware is hooked up, here's your zero-to-hero checklist for the software. First, connect your VCC, ground, and data. Second, hop into the Arduino IDE and install the one-wire and Dallas temperature libraries. Why? Because your Arduino needs these translators to make sense of the complex digital data. Upload your sample code, open your serial monitor at 9600 baud, and boom, you'll see crystal clear temperature readings updating every second. Now, if your readings are glitchy or you're seeing a weird -127 error, this is almost certainly why. You absolutely need a 4.7 kilo-ohm pull-up resistor. This is a critical engineering standard. It sits right between the signal pin and VCC power. Think of it as an anchor that stabilizes the data on your one-wire highway. Skipping this little component is literally the most common reason for failed sensor readings.
Section 4. The Raspberry Pi Communication Barrier.
So, what happens if we switch to a Raspberry Pi? Well, the Pi is a digital purist with massive computing power, but it's missing one key feature on its hardware, an analog-to-digital converter, or ADC. It only understands pure voltages, ones and zeros. That means the wavy, continuously changing voltage from the analog version of the KY-013 is completely invisible to it. The signal essentially hits a brick wall. But don't worry, we have a clever workaround, the KY-053 ADC module. It acts as a universal translator. You just drop this little board between the analog sensor and the Pi. It takes that wavy analog voltage, runs it through a high-resolution 16-bit chip, and turns it into perfect digital data over an I2C connection. Just like that, the communication barrier is totally gone.
Section 5. Setup and Debugging.
Okay, so you've built your circuit, but things aren't working. Don't panic. Just systematically run through this professional debugging checklist. First, verify your power. Are you getting that 3.3 to 5.5 volts? Second, did you remember that 4.7K pull-up resistor? Third, double-check your one-wire library is actually installed. Fourth, make sure the digital pin assigned in your code matches where you physically plugged it in. And finally, check for reverse polarity. Did you accidentally mix up plus and minus? Checking these details will save you hours of frustration.
Section 6. Real-world use cases. Measuring temperature is basically digitizing the physical world. It is the heartbeat of automation. You can't manage a smart home or run a modern automated farm without rock-solid temperature data. This simple little module we've been talking about is actually the foundation for some incredibly complex industrial systems. Let's look at how this plays out in the real world. In a smart home, these sensors manage your HVAC to save massive amounts of energy. In an industrial greenhouse, they optimize the exact thermal conditions plants need to thrive. They gather ambient data for weather stations. And in IoT monitoring, they track giant industrial freezers to guarantee food safety. Now, if you're running long cables across a huge greenhouse, you absolutely want the digital version to avoid signal interference. But for a quick, simple school experiment, the analog version works great. Knowing which one to use dictates the success of your entire project.
It really brings everything full circle. A few simple wires on a breadboard and a basic understanding of electronics can lead to engineering a massive autonomous system. Whether you're turning analog waves into math or reading precise digital bits, these are the fundamental building blocks of shaping the world around us.
You've decoded the identity crisis, mastered the wiring, and learned the debugging tricks the pros use. You now possess the blueprint to measure the world. The only question left is, what will you build? Thanks for joining us for this explainer. Keep building, and we'll see you next time.